Hello, welcome back. So in this part, we're going to look at a few more advanced deep learning architectures as they are being used for text processing, specifically recurrent neural networks and the so-called long short-term memory networks and sequence-to-sequence models. So here in this single lecture, we can only do this on a rather high level. For more details on how they work, you would have to go, well, either study on your own or take a machine learning or a deep learning course. But you'll get the idea how they work and how to apply them using the libraries that we already discussed. So one issue in natural language processing is that, as we discussed earlier, the order of the words is important. If you look at two sentences like this, the stolen car sped into the arena or the clown car sped into the arena, they have two quite different images, two quite different meanings behind them. And the point is that at the end of the sentence, you have to sort of remember what happened earlier to get the overall picture. So with CNNs, basically we fed a whole sentence into the network. Here, what we're going to do is we have a neural network where we feed one token at a time into the network and give it the ability to look back at the previous tokens. So that's the idea of a recurrent neural net. The basic part is just like before. It's a feed-forward network, input layer, hidden layer, output layer. The new thing now is that we have a loop in there. And what we do is we take the output from the hidden layer. It goes to the output layer as usual, but we also give it as an additional input at the next timestamp to the hidden layer. So timestamp because we go one token at a time. So if you unroll this, you look at it from a temporal perspective. We're going to go one word in the sentence at a time. We start with the first word. Again, using word embeddings, goes into the input layer, hidden layer, output layer. Then the next time step, we are going to look at the second word in the sentence, goes into the input layer. Result goes into the hidden layer, and a second input is the output from the hidden layer that we computed in the first word. And then so on and so on for the next words in the sentence. So at a single time step t equals 0, you can visualize it like this. We have our input vector. The input vector goes into the hidden layer. And then for each neuron in the hidden layer, we memorize the output for each hidden neuron. We keep track of it. And in the next step in time, we feed in the next input into the hidden layer, and now also the output from the hidden layer at time step equals 0. So it's like another set of inputs that goes into the hidden layer. So now, if we apply this to text, what we want to process is a sentence like this. It has to go into the hidden layer. And we want to do some kind of label prediction for this text. So the way it's going to be processed sequentially is we start with the first word. It goes into the hidden layer. It goes into the output, but at this point, we're not interested in the output. Rather, we keep processing until the end of the sentence. We take the second word, goes into the hidden layer, and then, like explained before, this hidden layer has an additional input, which is the output from the hidden layer for the first word. So it remembers the previous words in the sentence. And then we have the third word, and then again, the output from the second word from the hidden layer, and so on and so on. And then once we're at the end of the sentence, then we look at the output from the hidden layer. Then rather than we process the output layer and do whatever we want with this sentence. So in all the intermediate steps, we don't really care about the output. There is an output. Yeah, it's a normal neural network. It produces something on the output layer, but the only thing we're interested in is the output from the last step. And this has kind of this accumulated memory about all the previous steps in that sentence. What exactly it's memorizing here is, again, learned by showing it training samples. So just like before, we have to backpropagate the error between what we wanted to predict and what the network predicted. And the backpropagation works kind of similar to how it works in the normal case. The main difference is that now we cannot just backpropagate it from output to hidden to input layer. We have to backpropagate it throughout this whole network to get the updated weights for this network. So when you try this out in practice, you can see that there aren't really that many more weights in the network as such. Yeah, we have the input hidden output layer, but because you have to do the backpropagation through all of these previous steps, it's significantly more training effort. So it's going to take a lot more time to train this than a normal non-recurrent neural network. How can you implement it? Again, using Keras on top of TensorFlow, it has an implementation for an RNN built in. So you can just add an RNN layer. You give it the number of neurons, the input shape, just like before, and you have an RNN layer in your network. Finally, there is another extension to RNNs, which are bidirectional recurrent neural networks. So these are able to process a text both forward and backward. Essentially, what they do is have two RNNs next to each other, one processed like we did in the forward fashion, and then a second one that's processed in a backward fashion. So it can propagate the error both forward and backward in time, and this way understand a sentence in both directions. Okay, so much for the idea of an RNN. And in the next part, I'm going to tell you about long short-term memory networks, LSTMs. See you then.